All right, so today we continue. We finish our Belman-Ford algorithm, we finish our Belman-Ford algorithm, and we begin two other problems that are related to shortest paths. So all pair shortest paths. Suppose you want to find shortest paths from every pair to every other node in the graph. That's all pair shortest path. We'll find a better way of doing that. Of course, you could just run the single algorithm from every single node. There's a better way. And then we'll also introduce, if either we'll watch the rest of Thriller or we'll introduce max flow min cut, the next technique that we're going to talk about. All right, so what about negative edge weights? There are certainly situations like last time, this currency problem that I introduced, in which graphs, the problem you want to solve will have graphs and the edge weights will be negative. In this case, for example, we were going to change each of the currency rates into logarithms, and then some of those logarithms would be negative, and we'd be looking for certain type of cycles that have certain properties that would represent situations in which you could make money from currency trading. So the problem we had, the old argument broke down. If you remember from the last argument we had, we made some statement like, consider any path from S to the node that we're considering, and we can show that the length of this path is going to be greater than these two values. But unfortunately, when edge weights are positive, we can argue that this quantity is greater than 0, but when edge weights are not positive, that quantity could be negative, and so we can't, for example, conclude that this would be just greater than du, which is what we needed to argue in Dijkstra, the condition that stated that the value du that we have would actually be the shortest path, the length of the shortest path. So the first idea we had, remember last class, we tried adding a constant to every node, to every edge. So take a graph with negative edge weights and make it into a graph with positive edge weights. There were some problems. The naive way for doing that is kind of tricky. For example, if the shortest path had 3 edges, and you added a constant to every one of those edges, then now all of a sudden you would have added 3 times that constant to that particular path, whereas some other path which might not be the shortest path but only had 2 edges would only 6 would be added to that. So you could get into a situation in which you come to the wrong conclusion if you just add the same constant to every edge. Now there are ways around this. One tricky thing is to add a different weight to every edge, such that all of the edge weights are positive, and every shortest path in this new graph corresponds to a shortest path in the original graph. That's kind of a nuanced way of doing it. We're not going to talk about that idea, although that idea does have merit, and that idea would be valuable, for example, if you're considering graphs in which lots of edge weights change all the time and you don't want to recompute solutions all the time. But what we're going to talk about instead, we introduced this variable short IV. We're going to use dynamic programming in order to solve this, which is the single source shortest path. Okay, obviously I call it single source. The next abstraction we're going to talk about in the second half of this course is when you have more than one source, in particular all source shortest path. But to solve the single shortest path, we defined this dynamic programming variable short IV. This was the length of the shortest path from S to V that takes at most I hops. And we were able to express this value, this dynamic programming value, in terms of these 4 equations, like that slide. And that brings us, the final observation is that the length of a shortest path is going to be at most V minus 1. If the length is more than V, there's a cycle in it. A cycle shouldn't be part of a shortest path. We'll put an asterisk next to that statement in about 3 slides. We'll come and revisit that. But if it's an actual shortest path, then its length can be at most V minus 1. And so that suggests the Belman-Ford algorithm, which starts like this. So what we do is we first initialize a few things. So sometimes I'll use arrow like this. What that means is assignment. And that's to distinguish assignment from equality. Equal is also assignment, but sometimes we use equal for testing equality. So that's why this arrow means set short is to be 0. Set short 0, comma v to be infinity. And now, we do a loop like this. So remember, at the end of this, we're actually going to try to compute. We want short v minus 1, comma v. Right, this notation, v slash s, that means to set v minus s. So just remove s from that set. So for every node except for that s, which is the source, we want to figure out short of v minus 1. See, the notation there is a little bit tricky. Let me change that just a bit. This is what we're actually looking for, short v minus 1, comma x, for every node in the graph except for the source. And so we're going to compute it by iterating over I, and then considering every node in the graph, and updating according to this equation. I think I have a better version of it written right here. So so the first observation I want to make to simplify this algorithm of just a bit, take a look at what we would actually do. So let's say D was our source right here. And we would consider every node in this graph. Let's consider G, for example. When we consider G, we would basically consider this edge and this edge, every edge that comes into G, and we would update short of 1, comma G with essentially these two values, computed this particular way. When we analyze, so this outside loop is going to loop over every single edge in the graph, every node in the graph. So then at some point would come to H, and then we would investigate these two edges which come into H, and then at some point we would investigate F, and we would investigate these two edges. What I'm trying to say is that instead of writing this loop in steps 4 and 5, by looking at every single, instead of looking at every single vertex, if I were to continue coloring this, as, for example, I'll take the next step. Once we come to C, we would investigate all of these edges, right? So what I'm trying to say is that eventually, after I've colored every single node, do it. Okay. So, you followed the way that I colored all of those nodes. The point that I want to make is that instead of looping over every vertex, we can loop over every edge. And that will do the same computation just in a different order. So instead of looping over the vertices, I could have said, well, let's consider this edge right here. What's it going to do? Well, it's possibly going to update short G. Right? Now let's consider this edge. Now let's consider that edge, etc. We can go through the edges in this particular order and just update. We'll just loop over the edges and update the particular short variable that would be updated if we looked at that particular edge. Does that make sense to everybody? So by changing the order of operations, the algorithm becomes something like this. Still loop from from I1 to V minus 1. And now for every edge, we know that that edge, if the edge is from X to Y, it's going to update short Y. And now short Y could basically be one of three things. Either the previous short I minus 1Y, its current value, because now since we're looking at all of the edges, we're going to change these values at a different time. Or, since now we're looking at this edge XY, the shortest path to Y could involve taking this last edge and then getting to X in I minus 1 hops. So you see how we sort of just turn, it's the same algorithm, we just are doing these updates in a slightly different order. Just like in dynamic programming, you select the order in which you compute the subproblems. Here we're slightly modifying the order in which we evaluate each of these relaxation steps, is what they're called. And when we do it this way, it's easy to see that the running time of the algorithm is just going to be VE. All right? So what we're going to do now is actually go over an example of how this algorithm would work. And if you brought your handout from last class, I'd like you to follow along here. I'm going to do the first two steps, and then just to make sure that you understand the algorithm, ask you to do the last step. So recall what we do here is we initialize, of course, the source. We're going to start from D again. And so D0, short D0 will be 0. And the rest of these values will be infinity. And now let's try to compute this column, which is basically going to be short 1 comma x. Okay? So just like this algorithm right here, we can go over the edges and figure out which values are going to be updated. So for example, let's go ahead and consider this edge right here. So what that says is that this basically says that short 1 of G should basically equal the min of the current value, which is infinity, right? Or short 0 comma D plus 5. Right? 5 is the weight of this edge from D to G. And so, of course, in that calculation, it's going to be very simple. G will be 5. And similarly, now we can look at this edge right here. And this edge is going to be short of 1 comma I is going to be min of infinity, or short of 0 comma G plus 2. But in this case, short of 0 comma G is what? It's infinity, right? So in this case, I is the minimum of infinity, and so there's no update to that particular node. That's still going to be infinity. And you can go through the rest of this. You'll basically notice that the only values that are going to be updated are the ones that are actually can be reached by 1 hop from D. So in particular, when we consider this edge right here, then H will get updated to 5 as well. E will get updated to 7. And B will get updated to 8. So after one execution of this loop, if you follow this equation right here, you'll basically get these values right here. Okay. So now, let me do one more step of this algorithm. So now in this second step, as we go through the edges, this will do no update, this will do no update. All of these basically result in no new updates. But if we were to look at A, for example, now let's consider node A here. Short of 2 comma A is going to be the min of its current value, which is infinity, or short of 1 comma B plus 10, or short of 1 comma C plus 12. And this, right here, you can see that short of 1B is 8, so this will be 18. And short of 1C is still infinity. If it's the same, I haven't actually, I don't copy anything new. So this is still going to be infinity, which means that short of 2A is going to be the min of these three values. It will be 18. And similarly, B will still be 8. C will still be infinity. Short of 2C will still be infinity. Oh, sorry. No, you're right. So this will be 4. F will be infinity, and I will be 7. So let me just make sure we've done that. Okay. So what I'd like you to do now in class with your neighbors is to fill out this column right here. Yeah? Spend 3 minutes filling out this particular column with your neighbor, just to make sure you know the algorithms. So keep note that in this graph, I've added these arrows. So these edges only go one particular way. And that's to reflect that the graph actually has directions, and still the algorithm works. Okay, so let's actually do this the way that we would have programmed it, with going over every edge. So there are only, let's say, about 14 edges, so we should be able to do this in quick time. So let's consider this edge right here. This would only change short g, and it will change basically 0 plus basically d plus 5. So this value, so basically this edge doesn't change anything. Similarly, this edge right here would change short I to be short g plus 2, which is 7, the same. Okay, let's consider now this edge right here. So that would change short h to be short I minus 4, which would be 7 minus 4, which is less than 5. So that's the first update that happens right here. This should basically be 7 minus 4, which is 3. Okay, now let's consider this edge right here, which would change short g to be short h, 5, plus 9, 14, so it doesn't change anything. Consider this edge right here. This doesn't change anything. Let's consider this edge right here, which would change short f, 4, to be 5 plus 6, which is 11, doesn't change anything. This edge doesn't change anything. This edge doesn't change anything. This edge doesn't change anything. Let's consider, this edge doesn't change anything. Let's consider this edge. This would change short a to be short c, which is 4 minus 12, which would be negative 8. So short a should be negative 8. Let's see, this edge This edge doesn't change anything because it would change short E, which is already at 7, to be C plus 3, which is basically still 7. And this edge, this edge doesn't change anything, and this edge doesn't change anything. Right? So as we go through these, you basically go through this loop just by looking at every particular edge and seeing how it changes. Did that make sense? Questions? If D to H was negative, no, because that change will be reflected on the next step. In particular, all you got to do, and this is going to be one, all you got to do is look at your previous step. This is short I minus 1 of x, and add the current weight. And if that value is smaller than your current value, so in this case, your current value is 18, you just have to check short C for minus 12 and see if that's smaller, and you just have to update. So if D to H was negative, then in the next step, this would get updated. I don't know if I'm addressing, if you have a different question. We should get no time like the present to get rid of it. No, the order in which you handle the edges does not matter in this algorithm. You can pick any order for these edges and just take the previous column and update to the next column based on that order. The direction. So this right here, this line right here, it's the weight of x to v. So when these edges are directed, when there's an edge from h to g of weight 9, then basically let's say 3 of g can take essentially short 2 of h plus the weight of h to g, right? If we look at the other way, the weight of g to h would be infinity because that edge doesn't exist in the graph. Question? So G, remember, your input to this problem, to the single source shortest problem, the input, we'll go all the way back, the input is a graph and a starting node. That's the input to this function. So that graph consists of V and edges, a set of vertices and a set of edges. You can represent those in different ways, and yeah, we're doing the computation assuming that you can see, we just, in the fast version of this loop, we just loop over all of the edges. So the assumption is that we can scan over the edges in order E time. More questions? So there are still a few details left for this algorithm. So the first one is that so first, notice everybody's made the observation that this row of the table only depends on the previous row. Right? Currently, we're storing a table of order v squared, right? That's how I've drawn this table. Of course, to complete this, you would basically get all the way to this particular column. So the first point I want to make is that notice that in this graph, in our execution, a current row only depended on the row right before it. So how might we change this algorithm so that it only takes order v space instead of order v squared space? Yep. So I think you're going to answer the question of how would you actually recover shortest path? Let's not talk about the backtracking. Right now, notice that in this dynamic programming problem, the table is taking order v squared space. Exactly. So, in particular, do you remember how we've organized Dijkstra's algorithm and breadth first search and Prim's algorithm? Each of them had this value d, right? ds. the key for that particular node. So we can do the same thing. Instead of having a table of short I comma j, for every node we can just store a single value. And then we can update that value just by saying, at every step, for every edge in the graph, update this value to be the minimum of its current value plus this particular point. Okay, so this kind of gets to your point about when you do propagations and so forth. If you want to do it in the same step, you can, as you scan over the edges. Okay, so this is just one simple optimization. Notice that when you are programming this now, this is really a 5-line algorithm. The second point I want to make, okay, so the running time, we've talked about that before. The second point I want to make is what happens if there are negative cycles in this graph? In other words, when do we know when to quit in this algorithm? So take, for example, this graph right here. What is the length of the shortest path from S to T? Yes, this is a trick question because it's not well defined. Because you can get from S to T basically by going 2 plus 3 plus 1. Notice this loop right here, 3 plus 1 minus 5, has weight -1. So you can just cycle here and get, in fact, this is how these currency people make money, by finding such cycles and doing that as fast as they can. So what will our algorithm do? So technically, in this case, there is no shortest path from S to T, because you can always find a shorter path by taking one more cycle through the loop. So what will our algorithm actually do on this case? Let's take a look. Okay, so by now, let's call these intermediate nodes A and B. So in the first step, all of these values will be infinity. In the second step, okay, A will be 2, this will still be infinity, and this will be infinity. Oh, sorry, I think I have to start. The table is just 1. This will be 2, infinity, infinity. This will be 0 to 5. This will be 0 to 5, 6. Now, run one more iteration of this algorithm. What basically happens? In particular, what does this box become? Why are there only, you mean in this right here? In this version right here? 1, 2, 3, 4, 5, 6, 7, 8, 9. There should be 8 columns. And there are 8 columns. And okay, so the point is that this graph has 1, 2, 3, 4 nodes. Okay, and the point is that a nice property of Belman-Ford's algorithm is that once you run it p minus 1 step, and you run it one more step, two things are either going to happen. Either nothing is going to change in that table, because there are no more shorts to pass, or some value is going to get, some value in that column is going to get small. And then after a few steps, some value gets shorter. If you conclude that there is a negative connection loop, there is some loop that has, there is a negative cycle in this graph. And so that's in particular how you can answer the question, is there a negative edge weight cycle in this graph? You can basically run Belman-Ford algorithm, V steps, and see if any column decreases in that last step. And of course, you can also use Belman-Ford's algorithm as a side effect in order to compute just all shortest paths in the graph. then it will always happen on step B for some node. Okay. So one more observation. What happens if after 5 steps, nothing changes? So you read 4 steps, you got some point, and in the 5th step, nothing changed. Let's say you got a 100-node graph on the 5th step, nothing changed. What would it do? Did something change on the 6th step? No, because in every iteration you're doing exactly the same comparison. So if between 4 and 5 nothing changed, then between 5 and 6 nothing is going to change as well. Because every iteration you're doing exactly the same operation. So this also gives you a rule for early termination. Inside Belman-Ford, you come to a point before in which nothing changes, and you can quit at that point. And you know that you have the correct answer to all of the nodes. If something has changed, then you need to run one more iteration, and you can do that. Right? Applications of this Belman-Ford algorithm. So, one very nice. So the point is that this type of algorithm is actually used on the. It's the basis for an algorithm on the internet used for routing packets. So on the internet, if I want to send a message to a local server from my phone, I have to push routers to intermediate nodes. I would like to send that packet along the shortest path. What do I measure? What do I mean by shortest path? It's certainly from here to mountain users as the normalized as the shortest path. But I don't want to put my message on a pigeon. What I want to do is actually figure out the latencies of each of the links on all of the networks that I can use. So certainly one network I can use is AT&T to the cell tower that's 2 miles that way, from all the way to AT&T's network station in DC, to AT&T's network in San Francisco, and then off to whatever mountain. Or I could use this building's Wi-Fi connection, hop to that network, and then use UVA's DSL connection to the internet and get it all the way to Mountain View and that sort of thing. Right? So what I'm looking for, edge weights in this internet graph are going to correspond to network latencies, and the time it takes for a packet, for example, to travel from A to B. And what we like to do is compute the shortest path for my packet to my final destination. Now, what would be, since edge weights in this graph are going, first of all, edge weights in this graph are all going to be positive, because you can't send packets back. Right? So what would be wrong with using registry routing? Because technically, registry routing only takes 2 feet instead of over each time. I'd like to use registry routing for our packets on the well, I can run registry routing for my particular node. Why not? That's the point. If we were to use registry algorithm, we would have to know about every single connection on the internet. Right? How did that work? We knew all the nodes on the internet. And then we took the one with the smallest, our smallest connection. We made a priority queue with all the nodes on the internet. We knew all of the edge weights on the internet. And we ran essentially a priority queue operation. And then we had a respect. The nice thing about Belman-Ford algorithm is that notice that each node, it's only updated by its neighbors. So this algorithm is naturally distributed. If we think of each node as having a processor and essentially sending messages, so in step 1, D is going to send a message, hey, I can get to you, and it takes 5 seconds. Great. In step 2, G is going to send a message to H and say, hey, D can get to me in 5 seconds, and I can get to you, G, in 9 seconds, so you can get to D in 14 seconds. If you imagine each of those updates, each of with this particular graph, this line right here, this Wx on the line plus dx. Every node can locally compute that and send it to y. So that's the basis of the first internet routing protocol. Every router basically knows its connections, and when it gets an update from somebody else, it updates this line right here and sends it on to its neighbors. So even though this algorithm takes longer time than Dijkstra's, it does not require a global view of the network in order to actually compute final paths. So at the end, D would have in its local memory essentially the distances to all the other nodes, the shortest distances to all the other nodes in the entire network. And so, in particular, you can do high-level routing in this particular way. Now, that protocol doesn't exactly work because, so in particular, the way I've described it is totally asynchronous. There's no round one of the updates, right? As soon as you get a message, you send a message to another node. So the protocol is updated in various states. If links go up and down, so a link goes down, and some node broadcasts, oh, this goes down, I can go on eventually, there's updated distances from it. And then it comes back up, and then it comes down and up and down and up and so forth. Imagine that sort of cycling leads to a situation where you never exactly get the shortest paths in the graph. And so, the early protocols were called distance vector protocols, and now there are essentially path vector protocols, where in addition to storing DV, you also store the path that you use to get to DV. So every node keeps track of DA, DB, BC, all the way, all of this. Every node keeps that entire row in the matrix, and it also keeps the path. So what I'm saying is that, of course, in real life, the protocols that we're using today to route on the internet are more complicated. If you're interested, you can take this networking class. You can also just search for path vector protocols and learn more about this. But they're all based on this Belman-Ford algorithm. So, okay. So, as I said at the beginning of class, a next generalization of Belman-Ford of single source is all pairs. So imagine you want to find shortest paths not just from D, but from every node to every other node. In fact, on the internet, that's kind of what you want to do anyway. So one solution run Belman-Ford from every node. And in fact, this is what a distance vector protocol is. That is what I was just talking about, internet routing. It is doing something like this. The running time of this solution is going to be what? Right? EV, which is the running time of Belman-Ford, times V. Right? So it's EV squared. And we are going to do much better than this. Okay? We can do better. And here we go. The insight here is to come up with the right problem. So this is also going to be a dynamic programming problem. And there's a little bit of subtlety. So here's what this, I'm going to introduce a new variable, a short ijk, and it's going to be the length. It is going to be the length of the shortest path from I to j that uses only nodes 1 through k as intermediates. Notice the difference. Short ij, the condition was the length of the shortest path from S to node V that uses only I hops. The number was basically keeping track of the number of hops that are made. Here, we're not going to keep track of the number of hops. We're going to keep track of the intermediate nodes, and that's going to be critical for the analysis. Your homework is going to let you do it the other way, and you'll see how the running time of that algorithm compares to this one. So if this is the definition, here is an interpretation, right? The shortest path from I to j that uses intermediate nodes 0 through k, it's either going to be, what's this top link? Spend 3 minutes with your neighbor trying to work out the definition of A short ijk. I'm saying it's going to be one of two. Okay, so there was a question about what does it mean? There was a question about what this restriction actually means. And that means that the only paths that you can consider are ones that travel between nodes 1 and nodes k. Sure. Yes. So in general, assume that the nodes in your graph are, they're not letters, let's just, as input, you're going to give them this array, right? So let it be like the 1, 2, 3, 4, all the way up to n. Yes. Yes, they're not connected to each other. Yeah. These are just the first, as you get a graph as input. So they come in some order. Consider that order. The first one, the second one, the third one, the fourth one. So what this variable says is, it's the length of the shortest path from I to j that only travels within the first k nodes in your list of all nodes in the graph. Yes, the order can be arbitrary, because eventually you're going to consider A short ij, n, which means what is the shortest path from I to j using any of the nodes in my graph. Right? So this is akin to saying, so next week I'm going to be out of town, and there are a few ways for me to fly. Right? I can either use the hub in Washington, right? So consider the hubs that are available to me, right? There are Washington, Atlanta, Charlotte, LaGuardia, JFK, and Chicago. 6 of them, right? In some arbitrary order. So I can look for flights that use this as a hub. I can use flights that use the first 2 as a hub, look for flights that use the first 3 as a hub, etc. Right? It's the same idea. So, no, they're also, I mean, your path has to follow graphs, but this is like saying, what is the shortest way for me to get from here to Mountain View through London Heathrow, right? There's no direct connection, so the only way for me to do is directly go there. Sometimes this value will be infinity, because these first k intermediate nodes don't help you do anything. Questions? The point is that when we define it this way, A short ijk is only going to have 2 possibilities. The best way to get from I to j using the first k nodes as intermediates, it's either going to be A short ijk minus 1, i.e. you get there using the first k minus 1 intermediate nodes, or you use k. This would be, what would this, from I to k, what should go here? I, comma, k, comma, k minus 1. So you can get from I to k using the first k minus 1 intermediate nodes, and then you can get from k to j using the first k minus 1 nodes. So the point is that you initialize this with, when k is 0, you just use the edge weights. And after that, you only have 2 values to consider for each of these values. In the Belman-Ford, you had to look at every neighbor. For every node, you had to look at each of its neighbors. So this agreed equation had many steps. In this problem, you only have to look at 2. And so in particular, I've written it in C here. I would have written it in pseudocode, but look at how short the algorithm is. Most of this is just initialization stuff. It tells you how to initialize the graph. This is the actual algorithm right here, these 4 lines. This is, so basically we're computing A short I, J, K. And we iterate over K from 0 to N, and then we iterate I over all of the nodes, and we just implement our equation. So literally, this is a 4-line program. And its runtime, as you can see, is what? When I write it this way, what is the runtime? Yeah, V cubed if we're looking at V as the number of vertices, okay? Which is much better than EV squared. Okay, so this is the end of the shortest path section. The next week, what we're going to do, on Tuesday, there'll be a guest lecture who will talk about max flow. This problem is fantastic. It's a very interesting problem. I'll give you the 2-minute summary, okay?